Hi everyone. Hope you're doing well at home. This is lecture 18, which is an optional lecture, but this is just a good opportunity to teach a little bit of material that won't be on the exam, but will be potentially on the homework, and also to kind of work out the kinks of these remote classes before we get really going with the good stuff. All right. So, as a quick reminder, this is material that was originally going to be on exam number 2, but given the situation, we're going to go ahead and make this optional. So today we're going to talk a little bit about elastic collisions, about a specific type of recoil collision known as the rocket equation, and we'll talk a little bit about center of mass, which is, in the context of momentum, will not be on the exam, but we'll come back to it later when we start talking about rotational motion. Alrighty. So, to reminder where we left off, conservation momentum, we've been talking about 3 major types of collisions. The big one that you keep seeing over and over again is completely inelastic collision. So that's when 2 objects move together, stick, and then stick together after the collision and then move together. Recoil collision is kind of the opposite of this. This is your explosions, this is firing a gun, things like that. You start off moving together, you end up moving separately. Those 2 were pretty straightforward. They were non-energy conserving collisions. So this is cases with conservation momentum, but not energy. And today we're going to talk about the last one, which is completely elastic collision. So that is a case where objects scatter while also conserving energy. So a couple of examples of this will be magnets. If you have repulsive magnets, that will scatter without costing energy. Springs, billiard balls, things like that. And the thing to remember about completely elastic collisions is that it's not new physics. You've learned everything you need to know about conservation of energy, conservation of momentum. The important thing now is figuring out how to apply those conservation laws in practice. All right. So we have one more piece of information, conservation of energy. And what I mean by this usually is conservation of kinetic energy. So technically, every bit of energy is conserved. If I have 2 particles colliding off a single spring, I put a spring in between them, then total mechanical energy is going to be conserved. But if we consider 2 billiard balls colliding, or I hit a baseball and I tell you it's an elastic collision, then that would be a conservation of kinetic energy because it's such a short process, there's really nothing else that can change. There's no spring that's changing, there's no gravity that's changing, so the only thing that's left is kinetic energy, and therefore we think of it as being conserved. So now we have 2 equations in general. Let's say we have 2 objects, A and B, that collide. We have conservation of momentum, which is this top equation, and we have conservation of energy, which is this bottom equation. So that's just saying the kinetic energy of object 1 before plus the kinetic energy of object 2 before is equal to object 1 after plus object 2 after. So momentum and energy are simultaneously conserved. And again, that's everything that you would possibly need to know for this problem. However, I could present it different ways, and how you use this will depend on the situation that I give you. So I'm going to do a couple of examples where you can see the various ways that they're used. Here's a good one. So in billiards, again, let's pretend it's an elastic collision. Imagine I needed to hit the 9 ball with the cue ball. So the 9 ball is this one labeled 9, the cue ball is this white ball, and I tell you the following situation. The cue ball starts off moving to the right with some initial velocity vi. The 9 ball starts at rest. After the elastic collision, they both move away at the same angle theta from the horizontal. So the cue ball is going to go above the horizontal, the 9 ball is going to go below the horizontal. Sorry about that. 9 ball is going to go below the horizontal. All right, so at this point, I suggest that you pause. You try to write down conservation of momentum, conservation of energy, component by component for conservation of momentum, because this is 2D, and try to see if you can solve for the angle theta in terms of V initial, V final, and the velocity of the 9 ball. Please pause the video if you haven't already done so. All right, so now I'm going to assume that you've done that problem. Let's do it together, see if you got the right answer. So again, with this problem, the important thing to remember is there's no new physics in the problem. What's new about it is how we're going to apply that physics. So here we go. We have the following situation. Initially, our cue ball is moving with some velocity v initial, and our 9 ball is stationary. And finally, after the collision, they're both going to be moving. We had the cue ball moving at v final, let's call it, at some angle theta above the horizontal. And the 9 ball is going to be moving with some velocity v9 below the horizontal. And as you may have noticed on the slides, I introduced the following axes as usual. X is to the right, Y is pointing up. This is all happening within the plane of the billiard table. All right, so if we want to set up our conservation laws, let's start with conservation of momentum. So conservation of momentum will require us to figure out first, what is the momentum of these two balls? Well, let's talk about initially. So initially, it's pretty straightforward. The initial momentum of the cue ball, which I'm going to call C, in the x direction. So velocity of the cue ball initially in the x direction is just mass times velocity. So the mass of the cue ball is little m. The speed is v sub I. And since it's all moving to the right, this momentum is entirely in the plus x direction. And everything else is 0. So for example, the cue ball is not moving in the y direction initially. So that's 0. The 9 ball is not moving in the y direction or x direction initially. So just as a vector, the 9 ball initially is 0 momentum. And so that's everything. This is our momentum for everything initially. How about after the collision? So after the collision, we have to do a little bit of trig. We'll talk about the cue ball initially. So the cue ball moves at some velocity v final at an angle theta above the horizontal. So here's this magnitude v final. Here's the angle theta. And as usual, we'll break this up into components of the velocity. So velocity final x, velocity final y. And do our usual bit of trig. Y is opposite the angle theta, so that's my sine. VFY is VF sine theta. And then, of course, VFX is cosine. VFX is VF times cosine theta. If I want to translate these into momenta, that's pretty straightforward. So this is for the cue ball, by the way. Let's add a C there for cue ball. So momentum, I just multiply by the mass. The momentum of the cue ball, the momentum of the cue ball after the collision final in the y direction is just mass times velocity, so that's m vf sine theta. And similarly, the momentum of the cue ball finally in the x direction is m vf cosine theta. Good so far? All right. So now let's do the same thing for the 9 ball. The 9 ball is moving down and to the right. So here we go. Break it up into components. This is V9. This is the same angle theta. And we have V final of the 9 ball in the y direction. V9, let's just call it V9 final y, and V9 final x. So it's the same bit of trig. The x component is cosine because it's adjacent. So the momentum is just going to be V. The momentum of the 9 ball final in the x direction is just the mass of the 9 ball times V9 ball times cosine of theta. Looks pretty much the same as the cue ball. And if we talk about the 9 ball in the y direction, it looks pretty much the same as the cue ball. So it's m v9 sine theta, but notice that it's moving down. So that's a negative sign. So here we go. Here are all my final momenta. Here's my only initial momentum. And then I simply need to equate them, component by component. So again, we mostly are doing one-dimensional collisions, but for two-dimensional collisions, remember that the momentum x is equal to the momentum x final, momentum y initial is equal to final. So we're going to do this piece by piece. Let's talk about the x component first. My initial x component of momentum is m times v initial. That's equal to the total final x component of momentum, which is mvf cosine theta plus mv9 cosine theta. Similarly, for the y components, initially there are no y components of velocity. So my of momentum. So this is my x component. For my y components, the initial momentum is just 0. So I'm going to set that equal to the sum of the final y momenta. So that's mvf sine theta minus mv9 sine theta. Notice that now the fact that it's moving down is important because that's what gives me that negative sign. Okie dokie. So now we're almost good to go. Let's start with the second equation. That's going to make my life really easy. Sine theta cancels because I can just divide it from both sides. M cancels because I can just divide it from both sides. And what I get is 0 is equal to Vf minus V9. Or in other words, Vf, the velocity of the cue ball at the end of the day, is equal to V9, the velocity of the 9 ball at the end of the day. So that's pretty nice. And we're going to go ahead and use this. We'll go ahead and make everything into VFs. So for example, in this x equation, I now have mv initial is equal to mv final cosine theta plus mv final cosine theta, which is just 2m v final cosine theta. In this equation now, I can go ahead and cancel the mass. It's on both sides of the equation. So what I get is that v initial of the cue ball is equal to 2 v final times cosine of theta. Okay, so this is good. It gives us a relationship between v initial and v final. But notice that we're actually supposed to solve for theta. This isn't quite enough because we don't know the actual numerical values of v initial and v final. And in fact, we haven't yet used conservation of energy. So now let's go ahead and use conservation of energy. All right, so conservation of energy tells us that the initial kinetic energy of everything together is equal to the final kinetic energy of everything added together. Individually, the energies are not conserved because there's a collision, but the total energy of the system is conserved. So if I write that out, it's actually pretty straightforward. Initially, it's just the cue ball that's moving, so that's kinetic energy 1/2 mass times the velocity of the cue ball, vi squared, is equal to plus 0. So this is the cue ball. Initially, this is the 9 ball. That's equal to the final energy. And so the final energy is 1/2 mass times the final velocity of the cue ball squared plus 1/2 mass times the final velocity of the 9 ball squared, but we've seen that Vf is equal to V9, so that's just Vf squared again. Okie dokie. So we have one equation from conservation of momentum. From this, again, we can cancel the masses. We can cancel these factors of 1/2, and what I get is Vi squared is equal to 2 Vf squared. Now if I plug in Vi is equal to 2 Vf cosine theta, I can also rewrite that as 2 Vf cosine theta squared, or in other words, 2 Vf squared is equal to 4 Vf squared cosine squared theta. And now the bit of magic comes in. I can cancel out the Vf squareds. I'll divide through on both sides by 4 and take a square root. So cosine of theta is equal to the square root of a half, or 1 over the square root of 2. And this is now something I can solve. So it turns out the angle in this case is the inverse cosine of 1 over root 2, which turns out to be 45 degrees. And notice this doesn't depend in any way, shape, or form on the velocities, on any other detailed property of the problem, but just using conservation of momentum and energy, we can figure out that theta is equal to 45 degrees. Okay, so that's the general way this is going to go. We're going to use all of our conservation laws. We're going to solve for the things that we're interested in. For one-dimensional collisions, there's one little additional piece of information that's going to make our life easy, which is this nice formula that VB2 minus VA2 in the x direction for one-dimensional collisions says everything is equal to negative VB1 minus VA1. So it's pretty straightforward to derive. I'm just going to sketch out the derivation here on the slide. We start out with conservation of momentum over on the left, conservation of energy over on the right. So initial momentum is equal to final momentum, initial energy is equal to final energy. And then the rest is just some algebra. So let's go ahead and do that. First off, on the right-hand side of the equation, I'm going to bring MA over to the left-hand side, MB over to the right-hand side. So I get MA times the velocity difference is equal to MB times the velocity difference. Similarly, on the other side of the equation, let me go ahead and erase that little line right there. Let me do the following. So over on the right-hand side of this equation, again, I've just rearranged to get MA on the left, MB on the right. And notice that I have a term that looks like VA squared 1 minus VA squared 2. So initial squared minus final squared. A squared minus B squared, you may remember, is A minus B times A plus B. So we're going to go ahead and factorize that. So I have MA times VA1 minus X minus VA2X, etc. And now the little bit of magic comes in. Take a look. MA times VA1X minus VA2X shows up in both equations. That is equal to MB times VB2X minus VB1X shows up in both equations. And so if these two things are equal to each other, it means I can cancel them right on out. And when I do that, I get VA1X plus VA2X is equal to VB2X plus VB1X. I can rearrange that. It is the formula that I've written. So here, the relative velocities, that's velocity of B minus velocity of A final, is opposite the relative velocity initial, VB1X minus VA1X. So here we go. Imagine the following situation where two carts of equal mass undergo an elastic collision. So we have a quick little video on this. I'm going to go ahead and show you the video before you solve this problem. Sorry, I can't do the demos. Like you guys, I don't want to get sick. So this gentleman is going to do this with these carts. So it's an air track, and these carts have repulsive magnets on them. So whenever he pushes them off each other, they're going to undergo an elastic collision. Maybe I can show you this one right here. Okay, so he's going to throw one cart off the other. They're going to undergo an elastic collision. All right, so what I want you guys to try to do is consider the following rather simple situation. Assume the carts have equal mass undergoing an elastic collision with initial velocities v1a and v1b, which could be in either direction, so treat those as signed quantities. All right, so imagine they undergo collision. What I want you to do is quickly try to figure out what are the final velocities. This is a good time to pause if you haven't. Okay, I will assume that you have tried to work through the problem, have an answer. Let's see if we can figure this out using our brand new formula. So again, the initial setup of this problem is that I have one cart moving to the right with velocity v1a. So initial, I'm labeling with 1. This guy's moving to the right with velocity v1a, mass m. And this guy is moving, let's say, to the right a little slower with velocity v1b. After the collision, final which will be labeled 2. So in the previous formula, 1 corresponded to initial, 2 corresponded to final. This guy's going to moving, let's say, to the right with velocity v2b. And this guy's going to be moving with velocity, this is v1b, v2a. Object A is moving final, which is 2. So this is v2a. One of the hardest things and one of the most important things in these problems is keeping your labels correct. So here we go, v2a, and the other object is moving to the right with v2b. So we have conservation of momentum, we have conservation of energy, and because this is a one-dimensional elastic collision, we have this magic formula, which is that the relative velocities switch. So I'm going to go ahead and write it out using the exact same language as I had before. VB2, or V2B, minus V2A, the relative velocities of these guys after the collision, is equal to negative V1B minus V1A, the relative velocities before the collision. Okay, so this is one of our equations. We want to solve for the actual values of V2A and V2B in terms of V1A and V1B. So we're not quite there yet. We have two unknowns and only one equation. Let's say I want to solve for these unknowns. I need one more equation. And the useful one in this case, well, you could use either conservation of momentum or conservation of energy that give you the same answer. We're going to use conservation of momentum. So this guy is like the special relationship for elastic collisions. We're also just going to go ahead and use straightforward conservation of momentum. The reason for that is it's a linear equation in the velocity, so it's velocity, not velocity squared. That's going to make our lives pretty easy. So our initial momentum is mv1a, momentum of A, plus mv1b is equal to mv2a plus mv2b. Okay, so initial momentum is equal to final momentum. And now we have two equations in two unknowns. That's something we can solve. In fact, it's pretty straightforward. So let's go ahead and do the following. I'm going to cancel out all my m's. We'll solve the first equation for, let's say, v2b. So if I want to solve the first equation for v2b, I'm just going to bring v2a over to the other side of the equation. And what I get out is v2b is equal to v2a minus v1b plus v1a. I can plug this in to my conservation of momentum. So my conservation momentum is v1a plus v1b, that's the left-hand side, is equal to v2a plus v2b, which we now know is plus v2a minus v1b plus v1a. And now a little magic happens. There's a v1a on each side of the equation, so I can get rid of them. There's a v1b here. I can bring it over to the other side. I get 2v1b is equal to 2v2a, or in other words, v1b is equal to v2a. If I plug this now into my previous equation, for example, this equation for v2b, so v2b is equal to, sorry about that, v2b is equal to v2a minus v1b, but we just saw that v1b was just v2a, plus v1a. Again, the v2a's cancel. I get that v2b is equal to v1a, and v1b is equal to v2a. So in other words, what's happening here is the carts will interchange their velocities. Whatever was the initial velocity on cart B becomes the final velocity on cart A, and whatever was the initial velocity on cart A becomes the final velocity on cart B. So let's see how this works in practice. For example, at 30 seconds in the video, we see what happens if v1b is equal to 0. So if the b velocity is equal to 0, that means it starts at rest, v1a is moving to the right, then after the collision, they'll exchange velocities. This guy will stop, and this guy will be moving with the same velocity as the other one started off with. So here we go. If we go back to our handy dandy video, should be at around 30 seconds. Aha, okay, so one of them stops and then the other one just takes its velocity. Everybody see that? One of them starts out stopped, the other one just takes its velocity. What about if they're moving opposite to each other? So if this guy starts out, A starts out moving to the left with some velocity and V starts out moving to the right, to the left with the same velocity, then after the collision, they're just going to reverse. So A is going to move to the left, B is going to move to the right. This one's a little harder to see, but I think we have an okay demonstration of this in this video. So he's going to do his best to try to throw these guys at each other with the same velocity. And here you go. Cheated a little there. So you can see, to the best of our experimental ability to do this, they will indeed exchange their velocities. Alrighty, so again, this is not on the exam, but that's pretty much all you would need to know if we were to have an exam. I like to give you guys slightly more challenging problems to see how this can get put together. So here's one where we can see how this can get put together. Imagine I have the following situation. Two heavy masses of mass m and 2m are attached to light rods of length L and held horizontally at rest. So I'm going to hold these guys horizontally and let them go at the same time. So what I want you guys to try to figure out is what are the speeds they have when they meet at the bottom, symbolically in terms of these quantities. What's the speed of mass m after the collision, assuming an elastic collision? And what will happen, I mean, if you're familiar with this sort of thing, this is kind of like these Newton's cradle things that you can buy for your office desk. What's going to happen in this situation is quite simply that these guys are going to collide and then they're going to bounce away from each other, right? And so if everything's done right, the little m is going to take more of that weight, so it's going to go around really fast. And so the question that I want you guys to try to answer is, does it have enough to go all the way around, to complete a full loop-de-loop, or not? All right, so this is a bit more challenging. Take a couple minutes here. Go ahead and pause the video, and when you're done, let's see if you got it right. Okie dokie. So here we go. I have two heavy masses attached to rods, and I want to solve for basically a few different processes. So this one's a little trickier, I'm not going to lie, but it's basically the same set of physics we've learned already, just applied in a slightly different manner. All right, so here we go. In this particular problem, there are a few different things that's happening. And as I always suggest, the first idea that you want to do in these types of problems is identify what are the most interesting pieces of time that I might want to care about in this problem. All right, so there's a very obvious one. The initial time, which I'll call 1, is basically just right after I release it, right? So time 1, which is my initial time, is just like right after I release the masses. And that's what we had drawn in the previous figure. So mass m is here, horizontally with a rod of length L. And then over here with the rod of the same length L is my mass 2m. Think for a quick second, what's the next point that we're interested in here? So for quite a bit, they're just going to fall down, and eventually they're going to collide. So whenever you have collisions like this, if you think about what conservation of momentum is telling us, it's telling us what happens right before the collision and right after the collision. During the collision, something's going on and we're not going to solve for that. But right before and right after, that's what conservation tells us. So time 2 is going to be right before the collision. And if you take a look at what's happening here, just before the collision, so our mass little m will be almost vertical. our mass 2m will be almost vertical. And if you take a look at their velocities, m will presumably be moving, will be moving to the right with some velocity which I will call v2. And notice if the x direction is like to the right and y is up as usual, this is entirely in the x direction, actually. Similarly, so this is v2x of little m, and our heavier mass will be moving to the left. Its velocity will be v2x, and I'm going to call that capital M for the heavier mass. So I'm just going to define capital M as 2 times little m. And that's what happens right before the collision. They're both moving at each other entirely in the x direction. So now, it will not surprise you that the next point of interest, time 3, will be right after the collision. And right after the collision, we don't really actually know what's going to happen. We're going to have to solve this using our conservation laws. But we can make a bit of a guess. We can guess that they're both going to kind of go away at some particular manner. So for instance, I'm going to assume that the initial speed of this guy will be to the left. I'm sorry, the velocity of mass little m will be to the left. That's presumably correct. And let's call that v3x little m. Again, it's just moving in the x direction right after the collision. And we don't really know what's going to happen with the 2m. Is it going to keep going to the left? Is it going to scatter off to the right? Let's guess that it's going to scatter off to the right, and we'll go ahead and solve this. And then finally, there's one other time that we're interested in this problem. So this problem asks us what's the maximum height this mass little m gets to. How high does it go? So the answer is, whenever it reaches its maximum height, we'll call that time 4. The maximum height of the mass little m. Okay? And that actually could be when it actually continues around through the loop-de-loop and hits its highest possible point. But we won't know that until we solve the problem. All right, so let's do this piece by piece. Part A asks, what are the velocities right before the collision? So here we know our initial point. Everyone starts at rest horizontally. And we want to know what's happening just before that collision. So between times 1 and times 2, what is conserved? Energy, momentum, both, or neither? Go ahead and mentally record an answer. Energy, momentum, both, or neither. So the answer is, in this case, energy is conserved and momentum is not conserved. Energy is conserved because the only forces acting on these masses, let's draw, for example, little m, the only forces acting on it are the weight and the tension from the rod. Now, the tension from the rod could do work, but because it's perpendicular to the velocity, as we've seen with tensions and normal forces, it tends not to do work. It does not do work in this case. So the only work is due to gravity, and therefore energy is conserved. Momentum's not conserved because I have an external force, gravity. And so, for example, when an object is in free fall, momentum is not conserved. Alrighty, so energy is conserved, and that means that I need to calculate the energies. Let's talk first about time 1. So time 1, I have 2 types of energy here. I have kinetic energy and gravitational potential energy. We'll do it for each object individually because each object individually has conservation of energy. So let's start with object lowercase m, the smaller mass. Its kinetic energy initial, kinetic energy of mass little m at time 1 is just 0 because it's not moving. What about the gravitational potential energy? So gravitational potential energy is, by definition, mass times gravity times the initial y coordinate. And here I have a choice. What do I want to call y equals 0? I'm going to choose y equals 0 to be this horizontal line where they start. So I'm going to call this line right here where they start y equals to 0. Just makes the math a little easier, but not necessary. And so my gravitational potential energy will also be 0. And you can quickly see that this is also going to be the same thing for the heavier mass. So my initial kinetic and gravitational potential energy for the heavier mass are also 0. Okay, what about final? When it comes down to the bottom and is about to collide, let's talk about object 1. So the kinetic energy of object 1 right before colliding, so this is time 2, so this is the smaller object at time 2, is 1/2 mass times velocity squared. And notice that I've told you that the velocity is by definition v2xm. So there you go, that's our kinetic energy. Gravitational potential energy is equal to mgy. And notice that if the rod is of length L and y equals 0 is the initial point, then when I hit the bottom, y is going to be equal to negative L. It's L in the negative direction. So this is mg times negative L. Similarly for object big M, the heavier object, the kinetic energy is 1/2 big M, which is 2 little m, times v2 big M squared. And the gravitational potential energy is again just its mass, 2m times g times negative L. So now we're going to use conservation of energy for each object individually. They're not talking to each other, so each has individually conserved energy. So in particular, let's talk about object 1. My initial energy is just kinetic equals 0 plus gravitational is equal to 0. So that's 0. My final energy is kinetic, 1/2 mass times v2xm, lowercase m squared, plus gravitational, which is negative mgl, and that's equal to 0. The m's cancel, and we can solve that the initial velocity in the x direction is just the square root of 2gl, as we've seen quite a few times at this point. So notice this is the positive square root because mass little m is moving to the right initially. If I talk about the heavier object, the same math holds. You'll notice that this guy actually doesn't care about the mass of the object, but now it's moving to the left. So v2x big M is negative square root of 2gl. So those are our initial velocities. All right, question number 2. What are the velocities right after the collision? So right after the collision, what's conserved? So during the collision, I should say, what's conserved? All right, so mentally record an answer. Is energy conserved? Is momentum conserved? Both or neither? All right, so the answer to this is both are conserved. This is a collision. So as usual with collisions, momentum is conserved. And it's specified in the problem that this is an elastic collision. So for an elastic collision, energy and momentum are conserved. And indeed, it's not just any old elastic collision, it's a one-dimensional elastic collision. Notice that everything's just moving in the x direction. And so now, lo and behold, we get to use our magic property that relative momentum is reversed. So I know my initial velocity of both guys, and now I need to use their final velocities using this formula. So here we go. we know our initial velocities, we know we know our kind of special rule, which tells us that the relative velocities interchange. So what that means is that v2x lowercase m minus v2x uppercase m is equal to negative v3x, let me give myself a little more space here, is equal to negative v3x lowercase m minus v3x uppercase m. The relative velocities of the two objects interchange with each other. On this left-hand side, I can go ahead and just plug in what I have. So that's root 2gl minus negative root 2gl. So that's 2 root 2gl is equal to, on the left-hand side, there's nothing I can do. v3x big M minus v3x little m. And for reasons that'll become clear, I'm going to go ahead and solve this for v3x big M. So I'll bring v3x little m over to the other side, and I get v3x big M is equal to v3x little m plus 2 root 2gl. Okay, good so far? All right. Next up, we need to talk about conservation of momentum. So again, remember, this special law doesn't override conservation of momentum or conservation of energy, and we'll generally need to use the actual momentum conservation laws to get this to work. So in terms of conservation of momentum, my initial momentum is the mass of the little object times its velocity, v2x little m, plus the mass of the big object, 2m, times its velocity, v2x big M. Let's actually just go ahead and substitute these values. This guy is root 2gl. This guy is negative root 2gl. That's equal to the momentum, the mass of the small object times its velocity at the end of the day, v3x little m, plus the mass of the big object times its velocity at the end of the day. But notice that v3 big xm is just v3 little x little m plus 2 root 2gl. The m's cancel from everything. And now we just need to do a little algebra. So root 2gl minus 2 root 2gl is negative root 2gl. That is equal to v3xm plus 2v3xm is 3v3xm plus 2 times root 2gl, that's plus 4 root 2gl. First, I'll bring this 4 root 2gl over to the other side. So I have negative 5 root 2gl is equal to 3 3xm. And divide through by 3, I get that the velocity of this guy after the collision is negative 5/3 root 2gl. In other words, it speeds up. Let me just quickly double check those signs right here, because, yeah, that's right. All right. So it started off moving to the right at positive root 2gl. Now it's going to be moving to the left at negative 5/3 root 2gl. So it's sped up. And the final part of this question is, does it do a loop-de-loop? So here, we need to talk about this process starting right after the collision, where we know its velocity, and continuing all the way up until it hits its maximum height. So that's process 3 to 4. Now this should be pretty quick, but again, I want you guys to think, is energy conserved? Is momentum conserved? Both or neither? So in this case, energy is conserved. And again, this reasoning is exactly the same as part A of the problem. I don't have any work done by tension. I only have gravity, so energy is conserved. All right. Momentum, again, is not conserved because of gravity. So let's go ahead and write out what's going on. At part number 3, the initial of this, My kinetic energy of little m is 1/2 mass times velocity squared. 1/2 little m times velocity squared. Well, here's my velocity. So if I square that sucker, I get 25/9 times 2gl. Do a little bit of math. My 2's cancel. I get 25/9 mgl is my initial kinetic energy. My initial potential energy is the same as I had before. So that's just mgy. And notice that my y coordinate is just negative L. So that's negative mgl. And at the end of the day, the pendulum bob reaches its highest possible point. So when you reach your highest possible point, as we've learned, the top of a trajectory has final kinetic energy, K4 little m, equal to 0. So it temporarily comes to a stop, whereas the gravitational potential energy is going to be that mass times g times whatever the y coordinate it is when it stops. So we'll call this y4 because this is where it goes at time 4. And again, we have conservation of energy, so let's go ahead and equate initial to final. So initially, my total energy was kinetic, 25/9 mgl, plus gravitational, negative mgl, and that's equal to my final potential, my final energy. So kinetic is 0, plus gravitational potential is mgy4. And notice there's a little bit of magic here again. The masses cancel out, the g's cancel out, and I solve for y4 is equal to 25/9 L minus L, or in other words, 16/9 L. 16/9 by the by is 1 plus 7/9, so that's about 1.7777, etc. times L. Now notice, this is actually not possible. This is what the math tells us, but then we have to use a little bit of logic. If this is the highest possible height, well, at the highest possible height, mass little m is going to simply be at a y coordinate of L. We can never really get up to 1.777 times L. So what that says is the mass, instead of being able to reach this maximum height, will go through the maximum, still have some kinetic energy, and will continue around in a loop-de-loop. So yes, it does complete the loop-de-loop. So there you go. Conservation of energy, conservation of momentum. Some versions of that are a little nicer than others. But in the end, it's really just applying the laws that we've already learned. Alrighty, so, I've discovered the issues with online classes. All right, so there's one other thing that I wanted to talk about. Again, in the context of momentum, this won't be on the exam, but we will actually talk about center of mass again later. So a very important concept in physics is this idea of center of mass. And the way that this is going to be thought of is kind of the middle of an object. So let's start out, forget about this formula, let's just start out with a couple of simple objects. So for example, I've drawn 3 different types of simple objects here, R1, R2, and R3. So number 1's a sphere. For a sphere, it's pretty clear what the middle of the sphere is. It's kind of the point right at the center of the sphere. And so that's the center of mass. It's the middle of the mass of the object. For a disk or a circle, again, the center of mass is going to be the obvious point. It's the point in the middle where kind of it's the middle of the object. And for example, here I have a rod. The center of mass will be halfway along the rod, assuming the density is constant. So the question is now, assume I have multiple objects, or assume I have some funky machinery part that's made up of a bunch of different things that are all tacked together by screws. Where is the center of mass? And the answer comes down to this formula. It's basically you sum mass times position plus mass times position over all the objects, and you divide by the total mass. The position of the center of mass is mass 1 times its center of mass plus mass 2 times its center of mass, etc., divided by the total mass. So this is loosely speaking the middle of the ensemble, the middle of all the objects tied together. And so in cases of symmetry, as I've mentioned, this is pretty straightforward. In the absence of symmetry, you just have to use this formula, solve for the center of mass, and there you go. So we'll do one quick practice example of this. Again, we'll cover it a little bit more detail down the road. But center of mass is actually really useful when we're talking about gravitation, when we're talking about movement of objects due to gravity. So consider the following gravitational system: the sun, the moon, and the earth. And at a particular point in time, imagine that their positions are as drawn. So the distance between the sun and the moon, the sun and the earth is 1.46 times 10 to the 11th meters. The distance between the earth and the moon is 3.844 times 10 to the 8th meters. The masses are given right here. And importantly, what we're also going to say is that for this particular choice in time, this kind of snapshot, the displacement between the sun and the earth is entirely in the x direction, and the displacement between the earth and the moon is entirely in the y direction. So take 2 minutes, see if you can solve what is the center of mass of this system. All right, so let's go ahead and see what's going on here. There's a pretty straightforward application of the formula that I was mentioning earlier. I have 3 objects. I'm going to go ahead and draw them again here. I have the sun, the earth, and the moon. Distances are a little bit exaggerated, but otherwise correct. Sorry about that. So here's the moon. And I want to know the position of the center of mass. So I'm given the masses of each object. I'm given the distances. Let's call this distance 1.48, 1.496 times 10 to the 11th meters. This distance is 3.8, what did I say, 3.844, sorry about that, times 10 to the 8 meters. And also we need to specify our coordinate system. So we'll call x the usual direction, y the usual direction, and we're just going to define the center of the sun as the origin of the coordinate system, which is going to make life a little easier. So the sun is at 0, 0, or more accurately, its center of mass is at 0, 0. The earth has a position which is 1.496 times 10 to the 11th. Is that in the x or the y direction? So it's in the x direction, and it's the positive x direction, so we're going to the right. That's positive x, 1.496 times 10 to the 11th meters. And notice that it's at the same y coordinate as the sun, so the y coordinate is just 0. Similarly, the moon. So the x coordinate of the moon is actually equal to the x coordinate of the earth. They're along the y-axis from each other. So the position of the moon is simply 1.496 times 10 to the 11th meters in the x component, and then this 3.844 times 10 to the 8th meters in the y direction. And now that I know all 3 of my objects, and just as a reminder, the position of the sun is just 0, 0, I just have to plug into my formula. So the position of the center of mass is the mass of the sun times the position of the sun plus the mass of earth times this position of the earth, plus mass of the moon, position of the moon, divided by the sum of the masses, which, by the way, is pretty much just the mass of the sun, because the sun is much, much larger than either the earth or the moon. And if you plug in some numbers, it turns out that the actual answer is 4.547 times 10 to the 5th meters, or about 454 kilometers, and 14.20 meters. So this is a fun little fact about the Earth-Sun-Moon system. The center of mass is actually very, very close to the center of the sun. So to give you an idea of how close, the radius of the sun itself is 6.957 times 10 to the 8th meters. So the distance to the center of mass, if here's I draw the sun, the distance between the center of mass of the sun and the center of mass of the Earth, Sun, Moon system is less than 1/1000th of the radius of the sun. So whenever you have a really heavy object, it's going to dominate the center of mass. When you don't have a heavy object, then you have a more interesting formula. All right, so center of mass, again, is basically telling us about the middle of a pair of objects. And the reason I mention it now is that it does play an important role if we think about momentum, or actually, really, we could have thought about it when we were talking about conservation of momentum if we really wanted to. So to see why this matters, let's talk about the velocity of the center of mass, right? So center of mass is a position. What's its velocity? Well, velocity is the derivative of position with respect to time. So I just take time derivatives. The mass is constant. The radius, or the position, gives derivative of velocity. So notice the velocity of the center of mass is just m1 v1 plus m2 v2 plus m3 v3, etc., divided by the total mass of the object. So you notice this is the momentum of object 1. This is the momentum of object 2. And it's divided by the total mass of the system. So if I rewrite this, what I see is that the total of mass times the velocity of center of mass is equal to the sum of the momentum of the individual objects. In other words, if I think about the momentum of the center of mass as just the total mass times the velocity of the center of mass, then the momentum of the center of mass is equal to just the sums of the momenta of each objects. Now, why do I care about this? Let's take one more derivative and see why this really matters. So dp dt, the derivative of momentum with respect to time, you may remember this was the force. So I'm going to go ahead and write that as mass 1 times acceleration 1 plus mass 2 times acceleration 2 plus mass 3 times acceleration 3. By the by, while you do need to know a little bit about center of mass, you will not need to know this derivation. This is just something that I want you guys to see once. At any rate, so let's take a look at this. Mass 1 times acceleration 1, well, that's Newton's law. This is Newton's law for the total force acting on object 1. So if I break that up, there's whatever external forces acting on object 1 plus the internal forces. So for example, there's a force between 2 and 1 that acts on object 1. Similarly, for the force on 2, there's the external force acting on 2 plus the internal force between 1 and 2. And now you see a bit of magic happens. Again, because of Newton's third law, F2 on 1 is negative F1 on 2, meaning these guys cancel each other out. So the conclusion that we reach is that the time derivative of the center of mass momentum is equal to the total external force. In other words, the center of mass will just move as if it's acted on by all the external forces. So gravity, for example, acts on all of these objects. The center of mass will move as if it's being affected by gravity, or if everything's being acted on by a spring or something like that. It's usually gravity in these types of problems. So to give you kind of a fun example of this, imagine I shoot a shell and it does projectile motion. Halfway along, it explodes into two pieces. So we can, in principle, solve this if we use the recoil form of collisions. We can solve for velocities and solve for projectiles. But the fun fact is that you actually take these two pieces of the shell, the two fragments, and plot their center of mass, so kind of the halfway point in between them. It's going to just keep moving along as if nothing happened. It continues to move along as if there's only those external forces, in this case gravity, acting on the object. So that's kind of cool. It turns out they're actually really useful examples of this. So this, again, the final equation you need to know, the derivation is not so important, but I want you to kind of see how this works. So rockets are a really nice example where, let's forget about gravity. Let's just imagine a rocket's out in the middle of outer space and there are no external forces acting on it. So by the previous formula, if force external is equal to dpcm dt, then if force external is 0, the center of mass momentum will be constant. But that's kind of cool. So the way rockets work is as follows. A rocket has some mass and it's moving with some velocity. And what it's going to do, it's going to shoot fuel out its back. So for example, in rockets that go to space, those are hydrogen and oxygen that burn off each other. They're shooting out flames. That's your fuel. At the back end, at a relative velocity Vx, which is like the expulsion velocity, that's what it's called. So imagine it shoots out just a little burst of fuel, a small amount of mass delta n at this relative velocity V expulsion. So you can think of this like a collision. Before the collision, the whole object, rocket plus fuel, was moving forward with velocity v. And after the collision, the rocket is now moving with some slightly different velocity, presumably faster. A little bit less mass because it lost the mass of the fuel. Meanwhile, the fuel is moving backwards, so the fuel has mass delta m, and it's moving backwards at relative velocity Vex, V expulsion, so that's V minus Vex. That's the velocity of the fuel. And now let's go ahead and use this idea that the center of mass momentum is constant, or in other words, that momentum is conserved. So I'm going to go ahead and talk about the initial momentum in the x direction and the final momentum in the x direction. So initially, I just have the mass of the rocket times velocity v. The final momentum is the mass of the rocket that's left times its velocity v final plus the mass of the fuel times its velocity v minus v expulsion. And now I just need to do a little bit of math. So here we go. I've just reproduced those formulas, used conservation of momentum, or equivalently this statement about external forces, to say mv is equal to these two terms. Now we're going to just do a little bit of algebra here on the board. Again, you don't need to know this derivation, but it's kind of fun to see once. So the first thing we're going to do is we're going to isolate v final. So we're going to go ahead and bring the delta m times v minus v expulsion over to the other side of the equation. We're going to, I'm seeing there's a little bit of a mistake here. I should say v expulsion times delta m over m plus delta n. I'm going to divide through by m minus delta m. And I'm going to notice that technically this term right here should be m divided by m minus delta m. But m is much, much larger than delta m. So I'm going to actually get rid of those small little delta m. So this becomes 1. This becomes delta m divided by m. Okay, so let's go ahead and rewrite that formula. Oops, what did I do? Oh, the fun of remote classes. All right, so I'm going to go ahead and rewrite that formula really quickly. V final is v minus v delta m over m, using that small approximation. And now I'm almost done. What I now want to say is that v final minus v, so I'll bring v over to the other side, v final minus kind of v initial before this collision is equal to negative v times delta m over m, or in other words, m times delta v, so I bring the m over, that's m times delta v, is equal to negative v times delta m. M delta v is equal to negative v delta m. Go ahead and erase those stupid dots. There we go. And now with just a little rearrangement, I can divide through by delta t, the amount of time that this takes, some really short amount of time. And in the limit, where this is a very, very quick process, so the limit delta t goes to 0, notice that this now starts to look a lot like Newton's equation. So on the left-hand side, I get mass times acceleration. And on the right-hand side, I have some bizarre equation, negative v dm dt. So that turns out to be this new force called the thrust force. If mass is lost at a rate dm dt for an object moving at velocity v, and this should be v expulsion, I apologize about that. These should all be v expulsions on the right-hand side of the equation. Then the thrust force is equal to the rate of expulsion times the rate at which mass is lost. And notice this negative sign is simply because I'm losing mass instead of gaining mass. So I get a new force because I'm emitting fuel out the back. And the way to think of this is kind of a bunch of different recoil collisions, one after another, as the rocket kind of continues to explode fuel. Okay, so that's the last little bit of momentum that we wanted to cover. As I mentioned, this will not be on exam number 2, but thank you for listening. And there will potentially be a couple of practice problems just so that you can, get some practice on these for homework number 9. I will be reaching out very shortly with more information about homeworks, about exams, about all the fun of moving to online. But in the meanwhile, everyone stay safe, everyone stay happy, and I look forward to seeing you, at least hopefully virtually and maybe even in person, soon. All right, stay safe.